Right, so Module 25 introduces one of the last major new topics that we'll discuss in this course, and that's the use of arrays. Particularly right now we'll work with numeric arrays. And arrays are all about being able to store collections of variables or collections of data that are very related to each other without some of the difficulties or sort of burden of declaring completely independent variables. So arrays are first introduced in chapter 7. Really is all about arrays. The things that we'll be talking about here are in 7.1 through 7.2. And just like with every main new topic, I like to sort of demonstrate how or why we really need this new topic called arrays. And to motivate this problem a little bit, let's imagine if we were asked to enter in or have the user enter in 5 numbers, and after they were done printing them, print them out, or print them in reverse order, or really print them in any order, it doesn't matter. And the thing that's difficult about this particular problem is that unlike some of the problems that used accumulation, for instance, if I had asked you to ask the user for 5 numbers and print out the average, in that type of a situation, you actually don't need to remember each number. You don't need to store every single number that the user is going to type in a variable. You can really just accumulate and at the end just print out the average. Now this is something different because when they're done printing or they're done entering in these numbers, I want you to print these values out. And reverse order isn't really the critical part of this. So how would you do that? Well, you know how to read in one number. So you could certainly get that. And then later on, put some comments here. After we read a bunch of them, we could print them out. That's easy. But if we were doing this multiple times, we would really have to repeat this. Right? We'd have to read in some other variable. Maybe we would call it something like x2. Maybe we call this x1. And then we could print it out. And if we wanted to do reverse order, we could print out x2. And again, if we carry this all the way through to 5 here, x3, x4, x5, we essentially have the same statement. There we go with the dreaded copying and paste. We'd have the same exact statement with the only difference being the name of the variable. And so that program would read in 5 separate variables into 5 separate values into 5 separate variables, and then print out in reverse order. So what I allude to in the slides here is, well, what if I wanted to do 10 numbers? What if I wanted to do 20 numbers? If we think back to the beginning when we looked at loops, we asked the same kind of question, and we realized that I think that was for what if you wanted to print out the first 5 even numbers or the first 10 even numbers, and we finally realized that if we can change these statements a bit, we can make a loop. But if we look at this program, there's really not much that we can do to change these statements into some common form. There's no way that we can make this just a loop that goes around 5 times, because we're using a different variable name each time. And there's no way to control the variable name using an indexer, right? An indi or something like that. There's nothing that we can do with a variable to change the variable name that we're accessing. So we're stuck with this. That's ultimately what arrays are going to help us do. Arrays give us a way to declare many variables, all with essentially the same name, but differentiated by numeric indexes, integers, indexes. So we're going to have a lot of variables all called perhaps x, but each one will be distinct from each other based on an integer value for an index. Of course, that integer value could be a variable when we use it. and it can be a variable controlled by a for loop. Right? So we'll eventually get right back to this question and implement this. So arrays. Arrays are here because programs often need to store collections of items. Typically these items, certainly you're going to have a lot of numbers, but when we say collection, we really mean collections of several items that are related to each other, that are somehow representing sort of the same thing. Keeping track of all these variables is very error prone, it's a headache, and we can't really loop correctly with them. If we look back at this program, even if we could figure out a loop, we'd have lots and lots of variables, right? And lots of variables lead to lots of errors just because of we're human and we type things wrong. So we want to actually use the same variable names throughout, but only differentiate between variables using integer indexes if we can. And so an array allows us all in one shot to declare multiple values or multiple variables all of the same data type. So to declare an array, right, just like you'd regularly declare a variable, you're going to say the data type, you're going to say the name, and it's just all the same conventions in terms of the name. And then how many do you want? The size. Right? The size goes in this bracket operator, and there should be a semicolon at the end of these, obviously. These are variable declarations. Once I create this, I will have 10 distinct integers, my array, separated by indexes, and I'll show you how we're going to use those in a second. We can create arrays of doubles, we can create arrays of characters. While it's not that frequently used, we can also initialize all three variables within the array. So if we say int array 3, we can use the curly braces to specify 3 specific integers to initialize this. So let's look at what this looks like in memory. When we declare an individual variable called x, we might assign it to the value of 6, but when we declare that variable, we know that we've got a specific slot in memory that whenever we talk about x, it'll be mapped to this variable. Same thing with y. When we declare a variable y, we get a separate spot, and if we say y equals 8, it'll change it. When we declare an array, called array in this case, and we declare it as a size 5, we are literally getting 5 distinct variables, totally separate from each other. They're not really necessarily tied to each other in any way, although they do happen to be right next to each other in memory, although that doesn't really make much of a difference from our standpoint. In its typical form here, of course, those variables are uninitialized, just like it would be if you said int x without the 6. If you said int x, you'd have a question mark here too. Again, we've seen the initializer, right? So we can, in fact, if we already know the values that are supposed to be in that array, we can specify all 5 of them there, and we would see those variables. Now, we know that we can change x by just saying x equals 10. We can see out the value at x by saying see out x. The next question that we need to answer is how do we actually set each one of these variables? Each one of these variables does have a unique name, but it's a combination of a common name, array, and an index. So to use an array, we use this index. Array 0, array subscript 0, is the name of this first element, or this first variable, and we'll call the individual variables in an array an element. Notice that it starts at 0. That's very important. The first element always is subscript 0, followed by subscript 1, 2, and 3. So if I create an array of size 4 with 4 separate values in it, the only valid indexes that I have is 0, 1, 2, and 3. Our numbering system always starts at 0 when accessing this. So we can say array 0 equals 46, and 46 would go here. We can say C out array 1 and negative 14 would appear. You can think of this as each one of these are distinct variable names, but these integers can be stored in variables, so we can use them as counters. It's kind of unfortunate that C++ used the brackets in the declaration and the usage. So when we declare an array, we use this square bracket to say how big is it, how many variables do I want? I want 4 variables. When I say cout array subscript 0, or when I say array subscript 1 equals 6, to store the 6 here, when I'm using this, the square brackets are providing or are being used to show an index into the array. They're really not related to each other. It just so happens that we use the square brackets in both contexts, but it's important that you remember that when you're declaring an array, this is not an indexer, this is a size. When you're using the array variables, you use an index. So let's go back to our code and now think about writing this. I'm going to instead create an array called x of size 5. And I'm just going to replace this with what we would use in array notation. So the first value would go into the variable x sub 0, the first element in x. I've created an array of 5 integers. The next one would go in x sub 1. The next one would go in x sub 2. Remember, we start at 0, so the last one will only be x sub 4. We do not have a valid index at x sub 5. When we start to print these out, we'll have 4, 3, 2, 1, and 0. So now when we build this, we'll have no problem reading these values in. If we run it, we see our numbers print out in reverse order. Now, that doesn't really change anything. Obviously, it'd be just as hard to write this 10 times, but what we can very critically see is that this statement is only different from this statement by an integer. And if the integer is the only thing that's changing, we can store this I, or this 0, in a variable. So I'm going to say int I equals 0. And every time I do this, I'm also going to do I++. And now, you'll notice, because I starts at 0 and then I increment it, these can be replaced with literally the exact same thing. Over here I can say I equals 4, and I can print out x sub I and then do I minus minus, and I can do that 5 times, and I'll have the exact same output. If I build, exact same output, but now if I look at these statements, hopefully it's kind of jumping off the screen for you. You can write this as a for loop. I can say for int I equals 0, I less than 5, because the last index here was x sub 4. Remember, we have x sub 0, sub 1, sub 2, sub 3, sub 4, so for all 5. And we can do our I++ right in the for loop. So now, I need that. We've been able to collapse this entire thing into a single loop. And down here we can say for int I equals 4, while I is greater than or equal to 0, because we want to go all the way through until I is 0, I minus minus, and we just print out. So our program dramatically changes, or gets dramatically smaller now. If we run it, of course, we'll have the same results. If we wanted to change this to be 100 numbers, we could just change this to 100. We could change this to 100. And we change this, of course, to 99. The last element in an array with 100 elements in it is 90. The index is 99. Syntax rules. What can we do? What can't we do? If we look at this declaration of x, obviously that's just a regular variable. Size is a constant. What we're more worried about is these array declarations. I can declare an array of size 3. This is a variable declaration. That's fine. What I cannot do is define an array with a variable in its size. So I cannot create an array with anything other than a constant integer as the size. This will be a compiler error. I can use a literal variable as long as it's a constant. And this is actually a really nice idea. We use a constant in size, and we set the size to be whatever we need to do. And that way, when we go and we repeat the size over and over again through our program, and this would just be size minus 1, we don't run the risk of forgetting to update 1. So maybe we would do something like this. And now if I wanted to change this back to 5, I change it in one spot and only one spot. And that's really a helpful trick. So defining an array with its size as a constant is perfectly acceptable. Defining an array of size 0 doesn't make any sense. You don't get any variables. In terms of usage, in terms of accessing this, saying array1 equals 5 does not work. Array1 is not a variable. Array1 is a prefix, but without an indexer like this, right, this doesn't make any sense. We cannot assign the number 5. This does not assign the number 5 to all elements in array1 or anything like that. If I want to assign the first value, the first index in this array to be 5, this is how I would do it. I'd say array1 sub 0 equals 5. I put a question mark here because syntactically this is okay. Array sub 3 equals 6 would presumably store 6 in the 4th variable inside array 1. But if we look at array 1, we only have 3 variables. This is not a syntax error, but it certainly is a runtime error, and it could potentially cause our program to crash. This is called an array overflow or an indexing overflow error. It's actually one of the principal causes for most security flaws in programs. So I just wanted that concept is important enough that we should highlight this a little bit. When I say int a of size 5, we know that we are getting an array with 5 elements. Index 0, index 1, index 2, index 3, index 4. If I say A3 equals 4, that's going to put the 4 in index 3. If I say A5 equals 7, what this is really telling C++ to do is to go to the beginning of A, this is the beginning of A, and skip to the 5th part, the 5th variable. That would be where, in memory, that would be where that 5th element would be, that 5th index. And it would try to put that there. And that potentially is a major security problem. It's a security issue because we might have other variables there. That's not part of our array. Our array has been initialized to only include these 4 locations in memory. And so actually accessing an element number 5 outside the bounds of an array is illegal, and will cause problems. And in fact, another variable might be located there in memory. Likewise, if I say -2, that won't make any sense either. Right? We won't be allowed to do that either. Again, if I have a variable int x equals 2. I can say a sub x equals 9, right? And that'll put that here. And that'll put the 9 there. So I can have any expression inside these brackets. Remember the difference between the declaration is a size with the brackets, and usage, which is an indexer. All right, so continuing with this concept, I'll alter the program that I was working with here, and I'm gonna write a program that reads in exactly 10 numbers from the user, and then as a second part, I'm going to allow the user to type in indexes, so just integers. They're going to type in integers, and I'm going to print out the value of that number, or the value that is stored at that particular index. I also do some input validation on an index and make sure that it's within the bounds of my array, so I don't try to access an array or try to access an index that doesn't really exist. I'll wait until the user types in -1 as an index to stop the search. So it's just sort of populating an array and then kind of asking the program to tell me what is at what location. And in fact, to keep this a little bit more simple, I'm gonna probably just do this with 5, so I don't have to keep inputting 10 numbers. But nothing much would change if I did it with 10. In fact, I'll use constants to make it a little bit more convenient to change. So most of this can continue to be the same. I'll keep size at 5. I will read in my 5 values, but instead of just printing out arbitrarily, I'm going to now ask the user for an index. So I'm going to say int input, and I'm going to go do while input is not equal to -1. I'm going to ask the user to enter an index. I'm going to see in that index, or input. And I'm going to print out the value found at that location. So that would be x at input. So if the user types in 0, I'm going to be printing out the 0th element, the first item in the array. If the user types in 3, I'll print out the 4th element in that array. So I'll type in the same numbers as I was before. Now I'm going to ask for an index from the user. And if I type in 0, I get 3. If I type in, I should have an end of line here. If I type in 1, I'll get 4. You see 4 right there. Let's type in -1. That'll stop. However, we get this sort of weird number out here. And the reason we get that weird number is because when the user types in -1, I went and tried to print out x subscript -1, and there was garbage to the left of that array. So let's fix this up a little bit. 1, I'll print out an end of line. But 2, I don't want to print this out if the input is not a valid index, right? So if it's less than 0, I'll say if it's greater than or equal to 0, it's a valid index. And if it's negative, if it's -1, or even if it's -5, it really is not a valid index. So if I go and run this now, again, 3, 4, 2, 1, 3. If I type in -8, it does not print out anything bad here. If I try to print out what's in index 2, I should get the value 2. Remember, this is index 0, 1, 2, 3, and 4. If I type in 4, I'll get the number 3. That's the last value. Now, if I type in 5, I get garbage again, right? And I'm getting garbage because this array is of size 5, meaning I've got array subscript 0, 1, 2, 3, and 4. And if I try to access x sub 5, that is going past the bounds of the array. It's going out here. So we need to actually limit the user. This is a size 5, so this works good for this example. We need to limit indexes not only to be greater than or equal to 0, but they should also be less than the count, less than the size. You could say less than or equal to 4, but it's probably more convenient, since you normally have a constant representing the size, to say while the index is less than the actual size, 5. So while if the input is greater than or equal to 0 and the input is less than size, then I'll print out the value. And maybe if I say else if input is less than -1, I don't want to yell at the user if they type -1, or input is greater than or equal to size, I'll print out invalid index. And that'll be a little bit more clear to the user why they're not getting a value to print out. So now if I type in -6 invalid index, 5 is an invalid index, 100 of course is, 1 is valid, -1 will stop the program. Okay, so we've sort of demonstrated a first example of using arrays, using indexes. And one of the things that one of the harder concepts to get right in the very beginning is that we're not necessarily used to counting at 0. So knowing that it's greater than or equal to 0, knowing that it's less than size, in the for loop knowing that I equals 0, I less than size will take some time. But notice that this actually is the standard for loop that we've used in almost all of our examples. The reason why for loops always started at 0, or the default way that I write them is to start at 0, is because arrays start at 0, and you probably always access arrays using for loops. It's kind of convenient the way this whole thing works out if you don't fight it. If you kind of embrace the idea that the first element is 0, that element, the index size, will be outside of the bounds of the array. Right? So if the size is 5, then the last index is 4. If you remember that and you embrace that idea, these things actually kind of work out very well. Everything in C++ is based on starting your numbering at 0, and there's some wisdom in that.